where do fractals fit in education? My first question is, what do you think of when you think of geometry? A lot of people would say point or line or plane or squares, circles, angles, right angles, complementary angles. But what about the natural world? Are there truly perfect circles in the natural world? Are there perfect cones or spheres? Is there anything truly smooth? We know that, like, in Euclidean geometry, we can zoom in on a circle and get a tangent line to that circle because it's smooth. But in the real world, when you zoom in on something, like tree bark, for instance, it gets rougher and rougher down to the atomic level. So I think what we're missing with Euclidean geometry is models to show roughness or jumps or irregularities, which would be fractals, where fractals come in because they can model that roughness. So my argument is that not enough people really know about fractals. I told a lot of my friends here what I was researching for this class, and a lot of them, surprisingly, were like, "What's fractals? I've never heard of that before." And it surprised me, being at like an engineering school, that some engineers had never heard of it. So what is a fractal? The Oxford definition says it's a curve or a geometric figure, each part of which has the same statistical character as the whole. And they're useful in modeling structures where there's very similar patterns occurring over and over again at smaller scales, so lots of iteration in that. Fractals are a pretty recent mathematical development. It started kind of in the latter half of the 19th century. There were mathematicians like Georg Cantor and Helga von Koch and Giuseppe Peano and Wacław Sierpiński, and they were working on these weird fractal figures like this Cook snowflake here. They started just making these things by repeating patterns over and over again. And a lot of people weren't willing to accept these shapes. They called them mathematical monsters. They were really weirded out by, for example, this Cook snowflake here has an infinite perimeter but a finite area, which is just, they thought was so weird. So then Benoit Mandelbrot came along in the 1960s, and he kind of consolidated everything. He gave it terminology and kind of put a theoretical foundation for these fractals. And he recognized it also in the real world and was able to see where it applies. So that's a little bit of the history of the fractals, and these are a couple of examples. Fractals occur a lot in nature, as in the lightning and the fern up there. This triangle here is called the Sierpiński gasket, and this is a dragon curve that's similar to, I think Peano came up with a curve that fills every point in a plane, and this is a type of Peano curve. So to give a better definition of a fractal, a mathematical definition, we're going to look at dimension. Usually we have 1D, 2D, 3D, just dimensions that are whole numbers. But I will argue that you can have a dimension that is fractional. So just to be able to generalize dimension and get a definition for it, we're going to look at normal 1D, 2D, 3D, and we can basically come up with an equation that relates the scaling factor, the number of pieces when you scale something up by that scaling factor, and then the dimension of that. So if we start with a line segment, we know that's one dimension, and if we scale it up by a factor of 3, then 3 is equal to 3 to the first power. You have 3 pieces, and each piece is 3 times that length. So, or sorry, the 3 pieces together is 3 times the length of the first line segment. And that works for the second dimension and the third dimension also. And this also works for fractional scaling factors. If you scale it up by 2.5, then you're left with 6.25 squares. But we still know that this is a 2D object. So if that relates the number of pieces in the scaling factor with this equation here, and then you can solve for the dimension by taking the log of both sides and then dividing. So let's look at a self-similar fractal. So the border of the Cook snowflake, this is just a piece of it. This, at each stage, you scale it down by a factor of 3. So this piece right here is 1/3 the size of this whole thing. And then there's 4 pieces, 4n, in each new part. So the dimension is the log of 4 divided by the log of 3, which is 1.2619. It's a fractional number. It's not a real number. And so that was a very interesting thing that Benoit Mandelbrot came up with that kind of blew people's minds. Can we have a fractional dimension? Well, it's possible if you define it like this. And so this works actually just with self-similar fractals, but it applies in a lot of areas. So how can fractals actually be taught? This seems kind of complicated and weird, but I can argue that fractals should be taught as a comprehensive curriculum alongside Euclidean geometry, kind of as a comparison to it. And it can also be taught from the elementary school level onward, even to children. So I'm going to give some examples of how that can be done. For elementary school fractals, you can just show how it happens in nature by having them make a cut and paste fractal tree, which I made myself. So you can pass that around. This can work from kindergarten through the 3rd grade. Basically, it helps solidify the idea of self-similarity and iterations, and it helps connect fractals to nature, and it can also be modified to make a different shape, such as the veins in a leaf or a fern. What you did is just you start off with 4 strips of paper all the same size. For one of them, you make it the trunk of the tree, and for the rest of them, you cut them in half. Then you take 2 of those half pieces and make the first branch off of that. You take all the rest and you cut them in half again, and then have them glue the 2 or 4 actually smaller half pieces. And you take what's left, cut it in half again, and you start gluing those 2 on the very end. And you can keep going as long as you have enough room and their attention, but it's a very good activity because they can see that it occurs in nature. They can see, yeah, this is a tree, and they can also see the pattern behind it. And so a little later on in later elementary school, or even up through middle school, you can have them make their own fractal shapes, either from a line, like we saw the Cook snowflake here. We put a triangle in the middle third for the Cook snowflake. So they can develop their own fractals by putting in some different type, maybe not a triangle, but a different shape with that they can keep repeating again and again. It would probably be the easiest, like you wouldn't want to put a circle here because it's hard to make that self-similar, but something with straight lines, they could make their own fractal and keep drawing it all the different iterations over and over again. And that kind of leaves room for them to be creative. And then they could also do that from 2D patterns. They can look at a square and make some set rule for each iteration, like putting a square half the size on each corner. And then the next step, they put a square half the size on each corner again. As long as there's some set rule for each iteration, they can keep doing it, go and go for however long they can draw that small. And so they can do that on graph paper, or I just did this on GeoGebra. So that can be done on the computer too. And it gives them the opportunity to be creative and to discover these patterns for themselves. It also opens up the floor to discuss how these shapes are different from polygons. They're rough. If you keep going on and on forever, you can kind of open that up for discussion too. What would happen if you continued this forever? Maybe kind of help them start thinking about like, whoa, this is kind of weird. Can they even imagine the infinite process? So the goal that you would have for teaching fractals at the elementary middle school levels is to help them to see patterns and make connections with these fractals in nature, and also pique their curiosity. I think sometimes math seems a little dry to people when we're teaching it, and I think fractals are a really good way to help pique their curiosity and get them involved. And it also can offer an alternative, something to compare to Euclidean geometry, and it also would help them to identify fractals around them in the world and in nature. So on high school fractals, power laws are very important examples of fractals, and they occur a lot in nature. If you remember earlier, the dimension formula, n equals s raised to the d power, that was power law. And basically, it means that the relationship is invariant with respect to scale. If you change the scale, the relationship doesn't change between y and x. And that's because this exponent right here, that k. So in nature, it shows up a lot. Usually k is negative for the natural fractals. But A lot of examples of this would be earthquakes, maybe the distribution of income among people, the number of cities with a certain population. These are all power laws. And the important thing to notice is that this would be what the power law here would look like graphed if k is a negative exponent. But then if you take the log of both sides and graph it, then you're going to get a straight line. And the slope of that line will be your fractional dimension. So a lot of these things you can plot on a log-log plot, and if you see that there's that linear dependence, linear relationship between logs, then that is a fractal. It's a power law. So Benoit Mandelbrot, he was able to notice this and measure the coastline of Britain, which he claimed is a fractal. So what he did is he saw the power law relationship between the length of the coastline, which would be r here in this equation, and the ruler length that he used to measure the coastline. So if the ruler length is longer as he's measuring it, the length of the coastline is not going to be as long. But as he makes the ruler length smaller and smaller, the coastline will be longer and longer. And so he saw that relationship there. And if you solve for d and just take the length of the coastline with a lot of different ruler lengths, you can solve for the dimension, the fractional dimension of the coastline of Britain. So the log-log graph of this would give a straight line. And basically, if you take the log of both sides here, then the slope is going to be negative. So if you take the absolute value of that slope, then you get the dimension. And this blends well to another method of measuring the fractional dimension. That's the box counting method. So basically, it's the same idea. You just do smaller and smaller boxes rather than smaller and smaller rulers. And for this one, I found a leaf. This is actually not the same leaf because I had to have a really high, a very good picture of it. So I just found a picture online, but this leaf is pretty similar to the one up there. And so I took the picture of the leaf and I overlaid just grid lines on it, different sizes. And then you just count the number of grids that contain a piece of the border. And you plot that on a log-log graph and fit a linear regression to it. And this is what I did for 6 different box sizes and got a pretty linear slope there. I should have put the R value up here, but I guess I didn't do it for this one, but it fits pretty well. So I think that's a very interesting way to measure dimension, and that would be a good project for something like early high school students to do in Algebra 2. They can choose a leaf or a picture of a river, a satellite picture of a river or of a mountain range, or they can bring in a picture of a tree, and they can overlay the grid lines on it and count just where they show up inside the grids, and then plot their own log-log plot and fit a linear regression on it in either Excel or on their calculator, and they can come up with their own fractional figure and find the fractional dimension of it. And I think that would be a really interesting project for Algebra 2 students or high school students to do. And they can see that, wow, this really does occur in nature, and they can kind of connect the math behind it to the natural fractal. So you can see my leaf had a fractional dimension of 1.033, so it's actually, since it's so close to 1, it's actually not a very rough leaf, but it's still fractional. So another thing you can do with high school fractals is to have them code. If in a beginner coding class, so this can also be college level in a CS1 class, because fractals rely a lot on recursion or iteration, doing things over and over again at smaller scales. So this here is a Mandelbrot set that Mandelbrot came up with. Basically, you start out with a value, a complex number, and then apply this recursive formula to it. You square it and add it to itself again, and then take that and square it and add C, and then square that and add C. And you do it over and over. This is called a C process. And the Mandelbrot set is all values of C for which the C process stays bounded. So if it doesn't go off to infinity, then it's part of the Mandelbrot set, and it's one of these black points here. And so the different colors, the different shades here, are basically, it applies to the number of iterations it took to diverge. So one thing that we do know about the Mandelbrot set is that if the radius of that C value is greater than 2, then it will diverge. So it counts the number of iterations it took for the radius to be greater than 2, and they apply a different shade of color to that. And that's where you get the different values there. So the Mandelbrot set is very interesting. It creates beautiful pictures. And then there's another variation on it called the Julia set, and that's basically the same thing, but instead of adding C to it, you add just a set value, some complex number that you chose beforehand, and you do the same thing. And so basically you work through all the complex numbers in a certain box, in a certain range that you're dealing with, and you find which ones diverge and which ones converge, and you color the ones that converge black, and that is your Mandelbrot set or your Julia set there. So it's very interesting. It creates really beautiful pictures, and it would be it's not super hard for people to code, because I was able to come up with pseudocode for it, and I'm not a computer scientist, so if I can do it, I think CS1 kids can do it. Basically, you work through all the different complex values in a certain range and figure out if they diverge or converge. And if I have time at the end, I'll show you the program that I did to make you run one. I don't know if I'll have time, because I want you to be able to go, but and this is a really important part of Fractals, because they basically started to gain recognition when Mandelbrot started working with them on computers. And also, fractal programming is used a lot to make fractal landscapes. I think there's something they were saying about one of the Star Trek movies used coding like this to make a fractal landscape in the background. So they were pretty interested in that, and it's been used a lot now since then. And so this is another picture of that Julia set zoomed out. Okay, so the goal of teaching fractals at the high school level would be to be able to connect fractals in nature to the math behind them with those power laws, be able to see where the math comes out, to see the role that iteration has in fractals with that coding, and to kind of imagine what would happen if you were able to extend that process to infinity. On the computers, you can't go forever, you have to stop it somewhere. But just being able to, they can do a lot more than we can, so being able to see how far you can go with that is really interesting. And I think it's really important that you can connect the beauty and the art and the creativity in math all together. I think it's really important. So on to college level fractals. I'm going to talk about fractals and statistics, because they've been used a lot more recently in statistics. The power law distribution is pretty important. So I want to talk about the normal distribution a little bit. I want to argue that it doesn't work for everything that you're trying to model. A lot of times people try to either use a normal distribution or a version of that to model different types of uncertainty. But sometimes the normal distribution leaves out outliers a lot. It doesn't account for them. So sometimes you actually need to pay more attention to outliers if you're trying to predict something or trying to model something. And fractal scaling gives more weight to, or doesn't always discount, the outliers. And so in his book, Nassim Nicholas Taleb, in his book The Black Swan, talks about two different types of randomness, mild randomness and wild randomness. So mild randomness is a lot better for normal scaling, and that would be something like the distribution of height among people, or weight, or how many calories they consume per day, or something like that. Because you can't have a crazy outlier in that. You can't have a person that is many miles tall or weighs 1,000,000 pounds. It's not possible. It's physically limited. And so that would be a good case of mild randomness. But then wild randomness could be like moves in the stock market. You have huge jumps that exceed something like 22 sigmas in your normal distribution, which is basically impossible to have, but it's happened before, because different stock market crashes happen without precedent. You never know how big the next one's going to be. So, like I said, I wanted to give an example of the normal distribution uses and the power law uses. So estimating height can be done with a normal distribution. You're not going to worry about someone being miles tall, because it can't happen. But the distribution of income, one billionaire in a sample mean could throw off the entire sample. It would raise the mean too much, and it would just mess everything up. And a normal distribution can underestimate the probability of someone having a large income, but fractal scaling would be a better model or heuristic for that. And so here's an example of scaling. The basis is the power law relationship. So what's going on here is that if we know that the odds of being richer than 1 million are 1 in 62.5, and we choose a tail exponent of alpha over 2, then as the amount of money doubles each time, the incidence is cut in 4 each time. And the 4 comes from the scale, because we're doubling it, raised to the tail exponent of alpha. And this is just a very simple example. Alpha usually is found by doing the power law, doing a log-log plot, and finding that fractional dimension. But here they're just giving an example. This is what Taleb was talking about. So in this case, the ratio doesn't change with respect to scale, and smaller alpha gives you fatter tails, which means that a greater contribution to the total comes from low probability events. So it basically is a more conservative estimate of low probability events, because normal distribution, if you have a big outlier in there that really we know can happen because it has before, the normal distribution doesn't necessarily allow for that to happen, or gives it an extremely small probability. So it's hard to model with that. So an example of using a power law is in earthquake modeling. The Gutenberg-Richter law is a power law, and it says basically that the log base 10 of the frequency of earthquake greater than a certain magnitude, that's what that n of m is equal to log base 10 of A minus B times the magnitude. A and B are seismicity parameters for a certain region, and B is going to be close to 1. And then this doesn't look like a power law, because a power law is usually a linear relationship between logs, but we know that the magnitude is log base 10 of the amplitude over this A sub 0 of delta is basically correcting for how far the epicenter is from the seismograph. So it's basically the log base 10 of the amplitude. So that's how we get this linear relationship between logs, and we know that it's a power law. And then in the article I was reading, Turcotte says that the fractional dimension of the frequency of earthquakes is going to be 2 times B, and that comes from a lot of different random calculations with a lot of complicated formulas dealing with the relationship of the magnitude and the amplitude. So I wasn't going to get into that, but he says that the fractional dimension is 2 times B. So this Gutenberg-Richter law is a power law distribution of the frequency of earthquakes related to the magnitude. So basically, for a statistics project, you can take a lot of different earthquake magnitudes for over a number of years and investigate the power law dependence. Basically, would take the log base 10 of the frequency of earthquakes of a certain magnitude and plot it against the magnitude of those earthquakes. And that's what I did with this information right here. Over, I think, I did 905 different earthquakes that I found on the NOAA website, and plotted them, the magnitude versus log base 10 of the frequency, and got a pretty good linear fit there. So basically you can see that yes, there is power law dependence there, and if you want, you can look, maybe compare the Gaussian fit to your data and see like, oh, there actually is a difference between the probabilities there. So the goal at the college level of teaching fractals would be able to understand which models to use at what time. Do we use the normal distribution, or do we use something like power law scaling, maybe being able to recognize where certain things would work, and to be able to also identify fractal relationships on their own. So in conclusion, I want to say that fractals are everywhere. They're ubiquitous, so they're in nature. You can see them in lots of different places. And they're very useful for modeling and understanding the real world. But not enough people know about fractals. It's not in our education a lot. But they're really easy to incorporate into a good curriculum. From the elementary age onward, we saw, elementary students can understand this stuff. And so I would argue that fractals need to be taught more in our classes. Benoit Mandelbrot is quoted as saying, "Clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line." So maybe our thinking and our education should reflect that a little bit more. Any questions?
Do fractals show up at all in my Common Core stuff or the